Hello everyone, I am Dr. Rajesh and I am again with you with my next video lecture. And in this video lecture we have to find y(0) of the function y, which is given as log x plus root 1 plus x square. So how we will do it? We will first try to find the recursive relation between the derivatives and then we will try to find y(0). So as of now we don't know any nth order derivative of this given function, so we have no option other than differentiating both sides. So what we will get? We will get y1 is equal to differentiation of log will be x plus root 1 plus x square into, now this log have been taken into consideration. Now we'll differentiate x plus its argument. Differentiation of x is this one. Differentiation of square root of 1 plus x square is square root is 1 by 2. It will be root 1 plus x square. Now differentiation of 1 plus x square will be 2x. Okay, fine. So this further equal to 2 to 2 will cancel out. 1 by x plus root 1 plus x square into, now take the LCM, root 1 plus x square plus x divided by root 1 plus x square. So this differentiation is written of root 1 plus x square. Okay, because root 1 plus x square when differentiated can be written as 1 plus x square raised to the power 1 by 2. Now this 1 by 2 will come before 1 plus x square and 1 by 2 will become minus 1 by 2, by where minus 1 will be subtracted. Now this square root have been dealt with. Now we will be differentiating 1 plus x square. What is the differentiation of 1 plus x square? It is 2x. So this will cancel out and this is equal to 1 plus x square raised to the power minus 1 by 2 into x. This is equal to x plus root 1 plus x square. Fine. So this is how you do it. Okay. Now this will cancel out. So we are left with 1 by root 1 plus x square. This implies that y1, this goes over there, root 1 plus x square is equal to 1. Now we have to get rid of the square root, so we will be scaling both sides. We will get y1 square 1 plus x square is equal to 1 square is equal to 1. Now differentiate both sides, assuming this as u, this is v, their product rule will be applicable. I am going to remove this one, rub from here. So now differentiating again, what will get? Differentiation of y1 square will be 2 y1 y2, fine, and 1 plus x square as such, plus now 1 y1 square is as such. Differentiation of 1 plus x square is 2x and differentiation of 1 is 0. This implies that 2y1, it is 2y1, take it common, 2y1 y2 1 plus x square plus x y1 equal to 0, but 2 cannot be 0, y1 cannot be 0. This implies that y2 1 plus x square plus x y1 equal to 0. Okay, so now you will name the equations. Let us say this equation is named as number 1. This equation relation of y1 is 2. Relation here, this is named as 3. Fine. So simultaneously you keep on finding y1 0. So here if this is y1 and here no argument is given, so it is obvious that its argument is x. So if I at, because ultimately we have to find that x is equal to 0, so y1 at x is equal to 0, y1 0, when you put x 0 over here, 1 by 1 is equal to 1, so you have to keep this value saved. Y1 0 is equal to this one. Okay, y0, put it over here, 0 0, log 1, 0 1 plus 0 is 1, square root of 1 is 1, log 1 is 0. So if I say that y0 is 0, so this value will also be used. Similarly, find here y2 0. Here nothing is written. Can it be written something like, because its argument is x, 1 plus x square, it can always be written something like that, because y1 implicitly implies that y1 x. Now at x is equal to 0, what will get? Y2 0, 1 plus 0 is 1, plus x 0, this will be 0, is equal to 0, implies y2 0 is equal to 0. Fine. So I have saved these values and written them in the rectangular boxes. Now applying Leibniz theorem on equation number 3. So what is the statement of Leibniz theorem? Can we once again write it over here, that u v nth order derivative is equal to nc naught un v naught plus nc1 un minus 1 v1 plus nc2 u n minus 2 v2, and so on. It will continue something like that. So here in these two terms, Leibniz theorem will be used. One is in this term and this. So here this will be u, this will be v, and here this will be u and this will be v. So write differentiating three n times successively with respect to x, we get what it will be. It will be nc0 y2 n 0 order derivative of 1 plus x square plus nc1 n minus 1th order of y2 1 plus x square first order derivative plus nc2 y2 n minus 2 and second order derivative. Fine. Plus nc naught, this is y1 nth order derivative x naught plus nc1 y1 n minus 1 first order derivative. Applied the Leibniz theorem upon this, and after first order derivative of x, second order will become 0, third order. Similarly, third order derivative of 1 plus x square will become 0, so therefore only these terms are written, and here only two terms are written. This is further equal to 0. So now we will be writing it. nc naught is 1, nc1 is n, nc2 is n minus 1 by 2, so I am going to put the values. This will be 1, this will be y n plus 2 into 1 plus x square, fine, plus this will be n, this is y n plus 1. We have already done it. First order derivative 1 plus x square is 2x plus n minus 1 by 2. This is yn into second order is 2 plus this is 1 yn plus 1 into x plus n into yn into first order derivative of x is equal to 0. This 2 to 2 will cancel out. Fine. So now collect the terms yn plus 1 and yn plus 1, yn and this yn. Okay. So what we'll get, I'm going to write it over here. We'll get this will be y n plus 2 into one plus x square plus this yn plus 1 will be common. So here x yn plus 1 will be common. So it will be 2n plus 1 x yn plus 1 plus yn here will be common. So inside n square minus n plus n. So yn from these two terms is common. Yn is outside. This will go out. Okay. So this is yn plus 2 into 1 plus x square plus 2n plus 1 x yn plus 1 plus n square y n equal to 0. At x is equal to 0, y n plus 2 0 into 1 plus 0 is 1 plus here will be 0, anything multiplied with 0 is 0 plus n square yn 0 is equal to this one. This implies that y n plus 2 0 is equal to minus n square yn 0. Fine. Here we should mention what is the value of n, because we already know the values of derivatives for n is equal to 2, y2 and y10, which y1 is 1 and y2 0 is 0. So now from here after we should be determining y3 0, y4. So for that, if we have to determine y3, n should be 1, 2, 3 and so on. Fine. Yeah, I think it's fine. Okay, now put n is equal to 1 in above equation. What will get? y3 0 is equal to minus 1 square y1 0, and you know y1 0 here is 1. So I am going to substitute this is equal to minus 1 square into 1 is equal to minus 1. Put n is equal to 2 in this equation, and this equation could be named as, what is the last number that we have named? Up to 3. So this equation could be named as equation number 4. Put n is equal to 2 in 4. You will get y4 0 is equal to minus 2 square y2 0, and you know y2 0 is 0. So you just put it over here. This is 0. Now put n is equal to 3 over here. y5 0 is equal to minus 3 square y3 0. Fine. What is y3? it is minus 1. Minus 3 square into minus 1. So this will be minus 1 whole square into 3 square 1 square is equal to minus 1 square 1 square dot 3 square. Fine. Now put n is equal to 4. Here y6 0 is equal to minus 4 square y4 0. y4 is 0, so this will be 0. Okay, now put n is equal to 5. So what will you get? y7 0 is equal to minus 5 square y5 0. So this thing is equal to minus 5 square. What is 5 0? Minus, now you don't have to write it plus because we are moving towards the generalization. Therefore we have written y3 as minus 1 because here was only 1 minus, so it is written minus 1. Now here is also one more minus present, 2 minus, so I will not make it as 1 because we have to generalize. I have already told you many times that we don't multiply minus, but rather than we write it in the power so that we could get the generalization in the end. So this will be minus 1 square 3 square is equal to minus 1 into minus 1 square is minus 1 cube. So this will be 1 square dot 3 square dot 5 square. So this will continue something like that. Now we see for even it is 0, for 4 it is 0, this is 4, for 4 it is 0, for 6 it is 0, and for y2 it is also 0. You know, I can also show you here, it is also 0, and y1 0 is 1. Now look it over here, y1 0 is 1. Look at the pattern. When here is 7, minus 1 raised to the power 3, it's minus 1 raised to the power 3. Okay, minus 1 raised to the power 3, and running 1 square 3 square 5 square up to 2 less. Done. When 5, 1 square 3 square up to 2 less. Fine. So whenever here will be yn 0, so this will be 0 if n is even, and this will be like 1 square 3 square 5 square up to n minus 2, 2 less, 1 square 3 square 5 square and so on up to n minus 2 square. Fine. Done. Now see the of minus 1. Here is 3, here is 7. So when you just subtract 1 from the 7 and divide by 2, you will get it 3. You will get 5. Here is 2. When you subtract 1 from 5 and divide by 2, it will be minus 1 raised to the power 2, which is 2. So whenever here will be n, here will be n, so it will be into minus 1 raised to the power n minus 1 by 2 if n is odd. If n is odd, this is for n odd and this for n even. Fine. So this is what you were required to determine. This is yn 0. So for this we will have to determine the recursive relation. This is known as recursive relation, defining yn in terms of yn. This is the recursive relation. We have to find the recursive relation by Leibniz theorem. Then we put x is equal to 0 in the first order derivative. Whenever we determine it, immediately we find f1 0, because the problem here is to find yn 0. So as and when we determine y to x, we just put x is equal to 0 and keep this value saved. Okay, after that we determined that recursive relation, and here we replaced x is equal to 0, put x is equal to 0, then we get this recursive relation for x is equal to 0, where n is running from 1 to 3, because we already know the value of y1 0 and y2 0. So we, from this equation, we will be determining y3, y4 and something like. So we keep on continuing the values and we reached at this result. So this question was concerned with to find yn 0 when the function y is given. So this question is important from examination point of view. I hope that you will be able to understand this problem. So that's all I have from this lecture, and very soon I will be with you with my next video lecture. So till then, take care, bye bye, and see you soon.